A capacitor consists of two parallel plates, which explains why we use this symbol, or sometimes also this symbol here, for capacitors in electrical circuits. Let's assume we force a current IC through the capacitor. When doing that, charge will accumulate on both sides of the capacitor. That is, charge will accumulate on both plates. The difference in charge creates a potential difference, which is nothing else than a voltage, which we denote Vc. Due to this ability to accumulate charge, the capacitor can be used to store or deliver energy. The relationship between the voltage across a capacitor and the current through the capacitor is given by the characteristic capacitor equation. It is IC of t equals C times the first derivative with respect to time of Vc of t. Note that IC, the current through the capacitor, and Vc, the voltage across the capacitor, now both are functions of t. C is the capacitance of the capacitor, and its unit is farad, for which we use a capital F. The characteristic equation also yields the equation for Vc, which is Vc at time t is Vc at time t equals 0 plus 1 over c times the integral from 0 to t of the current. Hence, the voltage across a capacitor is the accumulation of the current through the capacitor. From this equation we can see that Vc, the voltage across a capacitor, has to be continuous. If the voltage would be not continuous, so that it would jump from one value to another at one time instance, the current at that time would be infinite. In order to understand better how the capacitor works, let's have a look at the discharging example. For this, let's assume that we have a circuit consisting of a DC voltage source, which produces Vs, a resistor, and a capacitor. Let's denote the current going through the capacitor as IC and the voltage across the capacitor as Vc. The voltage across a resistor is called VR. In DC circuits, capacitor acts as an open circuit. Hence, for a DC circuit, IC, the current through the capacitor, is 0, which also implies that no current is going through the resistor, and by Ohm's law, that means that VR has to be 0 as well. If we now apply Kirchhoff's voltage law around this loop, we'll find that Vc is Vs. Now let's assume that at time equals 0, we change the circuit. That is, that instead of connecting the resistor to the voltage source, we connect the resistor directly to the capacitor, so that the equations that we derived here describe the case before we switch. Now let's have a look at what happens after switching. If we apply Kirchhoff's voltage law around this circuit again, we see that VR equals minus Vc. Since we know that the capacitor voltage has to be continuous, we know that the voltage across a capacitor just before and just after switching has to be exactly the same. So Vc at 0 plus, which is the time just after switching, has to be the same as Vc at 0 minus, which is just before switching, for which we know that it is Vs. We also know the characteristic equation for the capacitor, which is IC is C times the derivative of Vc. Further, from Ohm's law, we know that VR is the same as IC times R. Combining all those equations, we see that the first derivative of Vc is equal to minus RC Vc. This is the first order ordinary differential equation for which we know the solution. It is Vc at time t is equal to e to the power of minus t divided by Rc, Vc of 0. And since we know that Vc of 0 is Vs, this is equal to e to the power of minus t Rc Vs. Visualizing the voltage across a capacitor gives the following plot. Up until time 0, the voltage is constant at Vs. After that, once we have switched, the voltage decays exponentially and approaches 0. The time that it takes until the voltage has reached about 37% of its original value is called the time constant, and it is equal to R times C. In order to get the capacitor current, let's go back to the characteristic equation. And substitute C by the expression that we derived above. Then we can see that IC is equal to minus Vs divided by R, e to the power of minus t over Rc. Let's also visualize IC as a function of time. Up until time equals 0, IC is 0. As soon as we switch, the current jumps to a value that is minus Vs divided by R, and then approaches 0 asymptotically. The time that it takes to reach 37% of the original value is again the time constant Rc.